You've probably been told that the ocean is rising because of climate change. When humans burn fossil fuels like oil and coal, greenhouse gases are produced, such as carbon dioxide and methane. These greenhouse gases make up part of our atmosphere, the gaseous body that surrounds our planet. The atmosphere helps to keep our planet warm. The Earth receives all of its heat and energy from solar radiation, from the light of our sun. When the Earth receives light from the sun, some of it is absorbed by land and water on Earth, and the rest is reflected back towards space. Greenhouse gases prevent the light, energy, and heat from escaping our planet. They trap the energy near the surface, keeping the Earth warm. We refer to this process of energy trapping as the greenhouse effect. The gases act like glass in the roof of a greenhouse. They let light into the greenhouse, warming it up even when it's cold outside. Greenhouse gases like carbon dioxide and methane are necessary for keeping and maintaining Earth's warm climate. In fact, they may be necessary for life as we know it. Many planets and moons in our solar system contain no atmosphere, or they contain atmospheres that contain very little greenhouse gas. In these cases, all the planets and moons are icy and barren, stark. Of course, the more greenhouse gas in the atmosphere, the stronger the greenhouse effect, and the warmer a planet may become. This is clear if we look at Venus. 96.5% of its atmosphere consists of carbon dioxide. It has been hypothesized that Venus may have been similar to Earth at one point. But today, Venus is hotter than any other planet in our solar system, even Mercury, which is closer to the Sun. The surface temperature on Venus is nearly 900 degrees Fahrenheit. The Soviet Union sent 16 probes to Venus and even landed a few spacecraft on the surface and acquired images of the planet. However, none of these landers lasted more than 2 hours before shutting down in the hellish landscape of Venus. Scientists attribute Venus's extreme temperatures to a runaway greenhouse effect. Back on Earth, carbon emissions are increasing the greenhouse effect on our planet and raising average global temperatures. Due to this warming, the polar ice caps are melting. Water that has been trapped in ice for thousands and thousands of years is flowing into the ocean, and sea level is rising around the planet. You can see clear evidence of this change. For example, many glaciers, which have been known for centuries and millennia, are now rapidly retreating and disappearing. It is important to understand that humans are partly or wholly responsible for climate change. We emit greenhouse gases, and greenhouse gases affect the environment around us. But it is also important to recognize that there are many natural processes that also cause changes in climate and sea level. Indeed, if we look backward through Earth history, we can see that sea level has been both higher and lower than it is today. It rises and falls over time. This graph illustrates two sea level curves, two different interpretations of how sea level has changed over Earth history. The horizontal axis represents geologic time. It shows the time in Earth history measured in millions of years. The vertical axis is sea level. It is measured in meters relative to today. 0 means that sea level is the same. Positive values indicate times when sea level was higher than it is today, and negative values indicate times when sea level was lower. In geology, We refer to a rise in sea level as a transgression, and a fall in sea level is called a regression. These have occurred throughout the history of our planet. But how exactly do we know about past sea level changes? What caused them? And what does Earth history tell us about climate change and rising sea level today? Given that historical geology involves the study of rock, it shouldn't be surprising to hear that we can learn about past sea level changes by studying sedimentary rocks. Recall that sedimentary rocks form through sedimentation, when particles of sediment settle out of air or water so that they are no longer in motion. As the clasts are deposited on the surface, they naturally spread out under the influence of gravity into layers called strata. Let's imagine pouring sands of various colors into a glass or some other container. As you begin to change the colors, you will notice that there are different layers. These layers record the sequence of events as you change going from black to white to brown and so forth. Even if you didn't pour the sand yourself, you could figure out the sequence of events. White must have been poured after black because it is above it. It's simple reasoning. If we look at sedimentary rocks, we can make the same assumptions. There is a key concept in geology called the principle of superposition. The principle is pretty straightforward. Generally speaking, when you are looking at horizontal strata, old rocks occur below young rocks. Young strata are superimposed on top of old strata. Consider how you might build a cake. The same principle applies. The lowest layer is the oldest. It obviously went down first. The uppermost layer is the youngest layer, with all other layers falling in between. Looking downward, we can look backward through the time. Before we return to the topic of sea level change, there is one last thing you need to know. Depositional environments change with the rise and fall of sea level. Imagine you are standing on a beach. Naturally, the sediment below your feet is probably sand. But what if you ventured further out to sea? What would you find on the seafloor? What would you find in different depositional environments where there is sedimentation? Generally speaking, most sediment in the ocean comes from rivers on land. Small clasts, like clay and silt, travel further and deeper into the ocean than large grains like sand and gravel. On the coast, you find beaches of sand. But if you venture further out to sea, you find that the seafloor consists of silt, and in the deepest water, of clay. This clay travels further out to sea than the silt or sand. Sediment grains also become rounder and better sorted as they are transported. So further from land, you are more likely to find mature sediment, well-sorted sediment with round grains. And of course, depending on how deep you are in the ocean, the sediment on the seafloor may be affected by waves and water currents and other physical processes. These processes can produce sedimentary structures. If you are on the continental shelf, where the water is shallow, the waves might produce ripple marks. If you are on the outer part of the continental shelf, or on the continental slope, where there are turbidity currents, you might alternatively find graded bedding. Suffice it to say that the lithology or characteristics of a rock depend on the water depth of its depositional environment. With this in mind, let's return to the beach. But this time, let's imagine that we could hit the fast forward button and accelerate the flow of time so that years pass in seconds. During a marine transgression, there would be an increase in sea level, and you would observe the ocean rise beneath your feet. The beach would become submerged underwater, and the coastline would move inland behind you. Ultimately, your beach would be lost to the ocean, and where you are standing would be covered by water. Of course, you would continue to see and feel other changes too. The water would be shallow at first on the continental shelf. You would be in a subtidal environment. You would always be covered with water, however, it would be clear and bright with sunlight. The sediment beneath your feet would still be sand, and you could still sense the motion of waves above you. Look around this part of the continental shelf, and you are bound to find a lot of marine life that only lives in shallow water, like kelp and seagrass. But as sea level continues to rise at your location, the water will become deeper, darker, colder, and quieter as you find yourself on the outer part of the continental shelf. You would eventually stop feeling the waves and seeing the sun. The sediment at your feet would turn from sand to silt, until you ultimately found yourself in the cold, frigid waters of the abyssal plain. There's no light down here. No waves either. You're too deep. You're now standing on clay and mud because you're too far away from the coastline for sand or silt. And as you can see, there's no marine life that forms down here. Only the sometimes bizarre and unusual animals that live deep in our ocean. You are experiencing the peak of the transgression now. Now let's think about the sedimentary rocks that were probably forming beneath your feet during this transgression. When the transgression started, the depositional environment was a beach. So the rocks that were being deposited at that time are beach facies. The sediment on the beach was sand, and the water was shallow, and there's probably waves and an array of shallow marine life forms around you. So you would naturally expect to find a sandstone with wave ripples and an array of fossils of seashells. We refer to this as a beach facies. A facies is all the characteristics of a rock related to its depositional environment. As sea level rose, there was a change in the depositional environment, so a new facies of rock was deposited. Let's call this the subtidal facies. It's the rock that was deposited when your location was always submerged below the waves and tides. This rock is probably also a sandstone. But the grains are much finer, and sedimentary structures may be less common. The fossils may be different. As time passed, you would have eventually found yourself on the outer shelf, far below the influence of waves. Here, far from the coastline, there is no deposition of sand, only silt and clay. There may have been turbidity currents in this location that could have produced graded bedding. Let's call this the outer shelf facies. Finally, when the transgression reached its maximum, you found yourself on the abyssal plain beyond the continental slope. Here, clays are deposited, and there are no sedimentary structures. Clay accumulates slowly as shale. This shale may contain fossils, but they would be very different from the ones you found in the beach facies. Let's call this stratum the abyssal facies. Now step back and look at your strata. They convey a story of marine transgression. From the lithologies and facies of the rock, you can tell that sea level rised over time. If you continue to observe sea level change from your location, you might have ultimately observed a regression as the ocean began to fall. If this were to happen, shallow water facies would have been deposited on top of your abyssal facies, and the sequence of events might have repeated itself in reverse. In any case, Scientists study past sea level change by examining changes in the lithologies and facies of rocks up and down geologic successions, such as this one. So then, what exactly causes sea level to rise and fall over time? Scientists distinguish between absolute and relative changes in sea level. Absolute changes in sea level are also called eustatic changes in sea level. They are observed and felt worldwide because they are caused by changes in the volume of the ocean itself. How does one change the volume of the ocean, you ask? There are two ways. The first way is to add or remove water from the ocean. Again, consider what happens when you melt the polar ice caps, ice sheets, and glaciers of our planet. Water that is freed from the melting of ice will travel to the sea down rivers and streams and cause the volume of the ocean to increase and sea level to rise. Naturally, the opposite is also true. If there is an increase in the amount of ice on our planet, the volume of the ocean will shrink and sea level will fall. Of course, there are other ways of adding water to the ocean as well. Freshwater lakes and ponds are separated from the ocean by natural and sometimes artificial barriers on land. If these barriers are removed, fresh liquid water may flow to the ocean. Consider the Great Lakes. The Great Lakes are located at a high elevation, hundreds of feet above sea level. In theory, if the barriers between these lakes and the oceans were removed by natural processes, water would flow downward under the influence of gravity and eventually add to the volume of the ocean. Sea level would rise. It would be just like adding water to a glass. The more you add, the greater the volume of the water and the higher the level. The other cause of eustatic sea level change is a little less intuitive. Let's continue to think about it in terms of a glass of water. The water is the ocean. The glass is the ocean basin, the low-lying area filled by seawater. Instead of changing the volume of the water by adding more or taking some away, we can change the size of the container itself. The same amount of water may have a higher or lower level depending on the size and the shape of the glass container. How does one alter the size and shape of the ocean basin? Ocean basins are always changing as a result of plate tectonics, the movement of the land masses across our planet. A change in the rate of this movement can cause a eustatic change in sea level. Land masses are driven apart by the creation of rock on the sea floor. When there is rapid spreading of land masses, it means that the planet is producing a lot of rock. This rock on the sea floor displaces seawater and causes sea level to rise. Conversely, when there is slow spreading of land masses, the ocean isn't producing nearly as much rock at the bottom of the ocean, and there is more space for water in the ocean basin, so sea level falls. This complex phenomenon will likely become easier to understand when you learn more about plate tectonics and continental drift. So, those are the processes that drive absolute changes in sea level. But what causes a relative change in sea level? Relative changes in sea level are changes that are observed locally. They are felt and observed in a specific place and region as opposed to all over the world. They are caused by the rise and fall of land moving upward or downward relative to the ocean. When land moves upward, we call it uplift. When land moves down, we call it subsidence. These things happen near faults. Faults are fractures in rock, where rocks can be displaced next to each other. Rocks on opposite sides of the fracture may slide past each other. One will move upward while the other moves downward. Uplift can be found at locations where mountains are forming. Mountains can form where two land masses or tectonic plates collide with each other. 50 million years ago, the Himalayan mountains began to form when a tectonic plate called the Indian plate collided with another plate called the Asian plate. At that time, the land masses were both located close to sea level. However, the collision caused the land masses to buckle, forcing the Asian plates to rise upward from the sea to higher elevations. Today, the Himalayas include the tallest mountains in the world, including Mount Everest. From the perspective of the land, there was a relative fall in sea level. Subsidence, or the downward movement of land, can be caused by earthquakes. In 2011, there was an earthquake off the coast of Japan, which created a devastating tidal wave or tsunami and caused many areas along the coast to sink. In some places, the landmass dropped by 4 feet. As a result, these areas became more susceptible to flooding during high tides and storm surges. In other words, there was a relative rise in sea level. Sea level seemed to be higher in Japan after the earthquake than before it. The timing of subsidence was particularly unfortunate. Areas along the coast were hit hard by the tidal wave. Another important cause of uplift and subsidence is isostatic adjustment. Isostatic adjustment occurs when heavy loads are added or removed from the crust, causing land nearby to be uplifted or subsided. Imagine adding ice, sediment, or lava on top of land. The weights of these loads would cause the land around them to rise and fall. For example, the east coast of the US is currently experiencing isostatic adjustment caused by ice sheets which formed during the last glacial ice age. This ice age lasted between 115,000 and 12,000 years ago. During the ice age, large ice sheets grew on top of North America. These ice sheets caused the land beneath them to subside and the land around them to be uplifted, creating large floor bulges near the coast. In particular, the east coast of North America experienced a lot of uplift. Then, 12,000 years ago, the ice sheets melted and retreated to the north. Since then, land has been rebounding. Without these ice sheets, land is returning to normal. The east coast, which was uplifted during the ice age, is now subsiding, and there is a relative rise in sea level. As you can see, our planet has experienced many changes in sea level over its history, and these changes reflect a variety of causes. In this context, it is important that we consider the history of our world. The past can help us understand what's happening on Earth in the present and help us prepare for the future. With this in mind, let's return now for a moment to the east coast of North America. The east coast is experiencing 2 types of sea level change: absolute and relative change. The east coast is still rebounding from the last ice age and is currently sinking into the ocean. That issue is compounded by climate change, which is causing the melting of ice, expanding the volume of the ocean, and causing it to rise around the world. Although isostatic adjustment is a natural process that cannot be stopped, climate change is one issue that could potentially be managed. It goes without saying that climate change is a complicated issue, and there is probably no simple solution. But given the number of people that live in coastal communities, particularly along the east coast of North America. It certainly makes sense that we exercise an abundance of caution and take care of our planet.